Have you ever wondered how a seemingly ordinary piece of metal can suddenly gain the incredible power to attract or repel other objects? It is like magic, but it is actually a fascinating dance of tiny internal forces that we are about to uncover. Magnetic domains align in magnets because it is the most energetically favorable state for the material. Think of it like a group of tiny dancers who naturally want to find their perfect formation. When these domains are aligned, the magnet settles into a stable, low-energy configuration, which is what all physical systems strive for. This alignment is the secret to a magnet's power. At the heart of this phenomenon are what we call magnetic domains. These are microscopic regions within a magnetic material where the individual magnetic moments of billions of atoms are all pointing in the same direction. Each atom has a magnetic moment, primarily due to the spin of its electrons, making it a tiny magnet itself. Now, imagine all these atomic magnets in a tiny neighborhood. There is a quantum mechanical effect, called the exchange interaction, that acts like a powerful neighborly agreement, forcing these nearby atomic magnets to align their spins parallel to each other. This strong internal force creates a small region, a domain, where all the atoms are perfectly lined up. While individual atoms want to align, the material as a whole tries to minimize its external magnetic field to reduce its overall energy. So, different domains form, each with its own direction of alignment, creating tiny north and south poles within the material itself. When an external magnetic field is introduced, domains that are already aligned with the field grow larger, effectively eating up their neighbors. Those domains that are not aligned will rotate until they too face. To create a permanent magnet, we essentially help these domains get organized. One common method involves taking a ferromagnetic material, like iron, and exposing it to a very strong external magnetic field. While in this strong field, the domains within the material are coerced into aligning with the field. Once the external field is removed, many of these domains will remain just locked in their new, aligned positions. This process can also involve heating the material above its Curie temperature, which is the point where the thermal energy is high enough to overcome the internal magnetic forces. Then, while it cools in the presence of a strong magnetic field, the domains solidify in an aligned state, effectively freezing the magnetism in place. These aligned magnetic domains are not just a scientific curiosity, they are fundamental to countless technologies. For instance, the information on your computer hard drive is stored by altering the alignment of these magnetic domains on a tiny scale. Each tiny bit of data, a 0 or a 1, corresponds to a specific magnetic orientation of a minuscule domain. This ability to manipulate and lock in domain alignment allows for reliable data storage. The way a material retains its magnetism even after the external field is removed is called magnetic hysteresis, and it is a crucial property for making permanent magnets and memory devices. So, the next time you see a magnet sticking to your refrigerator, remember that it is not magic but rather the collective, highly organized behavior of billions of tiny magnetic domains, all working together, driven by the universe's fundamental preference for the lowest possible energy state. It is a perfect example of how order on a microscopic scale creates powerful effects in our everyday world.